So last time we were looking at this case exponential forcing. So if you have a second order equation with an exponential function on the right-hand side, your particular solution, your initial particular solution form should be the same that you've been doing for first order equations. So in this case, it's going to be a e to the negative 2t. And this generally, I mean, if it works, then it's fine. But sometimes this will result in like a false statement, like 0 equals something. That was what we got right here. 0 equals negative e to the negative t. And you could try and plug it in your initial form and then discover that gives you a false statement and you get stuck. And then the solution was to multiply by t. But you can tell ahead of time this would happen if you compute your homogeneous solution first. And this one, because it's x double prime minus x, it's going to be r squared minus 1 is equal to 0. And you get r is equal to plus or minus 1. So it's be c raised to c1e raised to one of them, which is 1t, plus c2e raised to the other one, which is negative 1t. And then you look at the right-hand side and you're like, okay, e to negative t. So my initial solution guess for a particular solution would be a e to negative t. But wait, that's actually exactly the second homogeneous solution. So it's never going to have any hope of solving this differential equation because it'll solve the homogeneous equation instead. So that's your sign that you have to multiply by t. That wasn't a problem in this earlier one because if you computed the homogeneous solution, it gets the same equation on the left-hand side. So it's c1 e to the t and c2 e to the negative t. And then the right-hand side was e to the negative 2t, which doesn't look like an exponential that conflicts with any of these two. So that's why there was no issue. And so this whole multiplying by t will justify later, but it's not something so we saw it in first order equations because there we had to multiply by t as well. If you had like the coefficient in front of the x and the coefficient in front of the t on the right-hand side of the exponential were opposite signs, the same number, but opposite signs. And that I justified using integrating factor method. But for second order, we'll have to do something more to be able to see that. But if you do multiply by t and then plug it in, you have no issues. You don't get a false statement. You don't get any contradictions. And what I mean by contradiction is sometimes you get like your a is a non-constant. When you plugged it in, you assumed it was a constant. That's a contradiction. So you don't get these things if you multiply by t, but you do have to do the product rule. So your xp prime and xp double prime is a little more work when you plug it in, but you'll get successfully some constant for this undetermined coefficient. That ends up being your a with this t multiplied. So that's why this is your particular solution, negative half t e to negative t, plus your homogeneous that you had computed earlier. And then last time I just ended by saying if you were to apply these two initial conditions, this is your general solution. The general solution meaning that you have two arbitrary constants, C1 and C2, that are still arbitrary. But to solve an initial value problem, you need to find what your C1 and C2s are. That solves this particular initial value problem. But because there's two conditions, you need two constants, C1 and C2, you need two conditions. And usually they give you initial condition on the function, initial condition on its derivative. Of course, the derivative condition requires you to compute the derivative of this thing. And then you plug these in and hopefully you can follow this because this is just algebra and you get C1 and C2 are 3 over 4, 1 over 4. And those go into your C1 and C2 in your general solution. Okay, so now let's look at another exponential forcing function. So what I've done here is I took this equation up here. I kept the right-hand side the same because that's e to the negative t. And so here's also e to the negative t. So these two have the same right-hand side, but I changed the left-hand side. And so I like to do small modifications to things so that like you can see what repercussions arise from doing that. So because I changed the left-hand side, the homogeneous solution will now be different, right? Because if you're trying to find xh, you'll have to do the characteristic equation. And because I changed the left-hand side, it's going to be a different characteristic equation. And this right here, this factors to r plus 1 squared is equal to 0. Therefore, your r is equal to -1, but it's a double root because it's r plus 1 squared. So this is a double root. And we've done homogeneous second order equations. If you have a double root, your homogeneous solution, so I'll just say therefore your homogeneous solution will equal C1 e to the negative t will be one of them for sure. What's the other one going to have? C2. There's a factor that you add, right? Because it's a repeated t, right? Exactly. This should be not new because this was the previous section when we had a homogeneous equation. So that's your homogeneous solution to this. And it's always good now to do the homogeneous first, because when you propose a particular solution form, you may have to modify it by multiplying by t to make all the terms distinct from the homogeneous solutions. So looking at the right-hand side, your initial particular solution form you would think would be x of p is equal to, because it's e to the negative t, just a e to the negative t. But this has issues because this is going to match exactly with this, right? So essentially, these are the same. So this is like saying, this is my first homogeneous solution. We know this solution will satisfy this differential equation both with a 0 on the right-hand side. So if you try to plug this into this differential equation and get the left hand to equal this right-hand side, this e to the negative t, there's no hope. You're just going to get, I can tell you right now, you're just going to get a false statement. You're going to get 0 is equal to e to the negative t. And then, yeah, that's going to just get you nowhere. Just like we had here, basically, you'll get something like this. Z to the e 0 to the, I mean, obviously you're gonna, yeah, something like this. So the solution is to multiply by t. So you're gonna multiply by t. So that's the fix. So now if you multiply by t, you're gonna have a t e to the negative t, right? But are there problems with this one? Yeah. Because this is your second homogeneous solution. So there's no hope for this to satisfy your non-homogeneous differential equation up here. So if you try to plug this in, you're also going to get the left-hand side is equal to 0 because it's exactly this thing. You're never going to be able to find a coefficient capital A that will make this equal to e to the negative t. So what do? We multiply by t again. So this is just applying the same solution or fix that we've been doing. And so you'll get in the end a t squared e to the negative t. This now has no terms that resemble the homogeneous solution. So there isn't going to be an issue where it solves the equation with the 0 on the right-hand side. So this should work. But it required multiplying by t twice. So this would be the correct solution form. I'll use green. Correct xp. So the pain now is to just compute the derivatives of this. So what you're going to do is you're going to say, well, this is my xp. So this is like our correct xp. So just do this. So you're going to take this and compute the derivative. So you have to do the product rule. So your xp prime is going to be, so you're going to probably want to check this if you want later, but it simplifies to this. This is really just the product rule. And then it simplifies because there's going to be an e to the negative t that's common between all the terms. There's going to be two terms, and then there's going to be an a that's common, and then there's like one piece that's going to combine. So this is what you'll get. And then if you took another derivative of this is even more painful because it's like two product rules. And then there's a similar term that can combine in the middle of those. So then you'll end up getting a2 minus 4t plus t squared is e to the negative t. It's going to be super boring for watch me do the product rule on this and then do the product rule on this, because that's just a Calc 1 problem. But let's, assume that you're going to go back home and check that this is the correct derivative to this. The differential equation part of this class is like just plugging this into this up here. So you have x double prime. So what we're going to do is we're going to take this, and that goes into your x double prime. So this is like plugging in. And then you have plus 2 times your x prime plus your x, which is this one right here. It's this, xp that's been multiplied by t twice. And so that's the left-hand side, and this has to equal e to the negative t. All of these terms that are being added together have an e to the negative t in it, so you can just divide everything by e to the negative t. So this goes away, this goes away, this goes away, and this goes away. Of course, this side is just going to be equal to 1 after that. And then I'm just going to multiply out the left-hand side. So it's going to become 2 times a is going to be 2a minus 4at plus at squared plus 4at minus 2at squared plus at squared is equal to 1. And what's nice is that this minus 4at and this plus 4at cancel. This at squared has another at squared. So these two add up to 2at squared, but then there's a minus 2at squared. So all these red ones undo each other, which leaves us with 2a is equal to 1. So, I can just write this is 2a is equal to 1. Therefore, a is equal to half. And that leaves us with our particular solution is going to be this green box with a is equal to half. So you'll just get your general solution will be equal to 1/2 t squared e to the negative t plus the homogeneous solution, which I'll just copy and paste from up here. So this is your particular solution, so I'll use purple. And this is your homogeneous solution. But your particular solution had t squared in it. So that's because we had to multiply by t twice. And if you hadn't done that, you would have not been able to successfully find capital A. You'll just get like a false statement. You'll get 0 is equal to e to the negative t, right? And so the only painful part is just, honestly, it's just the derivative, xp prime and xp double prime right here. Those two are the painful part of this. Does it look good? Everybody feel good? Okay. So that's case 2. So case 1 was polynomial input function on the right-hand side. Case 2 was an exponential input function on the right-hand side, but there were subtleties. For both of them, there were subtleties. Essentially, if there are terms that match from your homogeneous and your particular solution, that didn't happen in this case, that happened once in this case, and that happened twice in this case. Each of those times you'll have to multiply by t to fix that, which we'll justify later. But for now, we'll just accept that that's what we do, and we've done that back in first order equations and justified it back then, but we'll justify for second order. For case 3, this is if you have a right-hand side that's not just an exponential, but it's actually like a polynomial. So this is like a degree 1 polynomial. Polynomial. And then there's also this exponential, right? So we've had one or the other by themselves, but what if you have a product of those two on the right-hand side? And so I propose that the solution form should be, maybe it's kind of intuitive. If you have a degree 1 polynomial times some exponential, it's going to be a general degree 1 polynomial times that same exponential. Now, why does this make sense? If I plug this in to the left-hand side, I should get terms that are going to resemble the right-hand side. That's the whole point of making sure you have a good solution form to begin with. The fact that you have e to the negative t here, even if you do the product rule, right? Because you have to do the product rule when you put it into x double prime or x prime, because this is something that's got t in it multiplied by e to the negative t. You'd have to do the product rule, but the product rule is like you take the derivative first times the second, so that keeps the e to the negative t. And then you take the derivative of the second, which is e to the negative t, but that'll pop out another e to the negative t times the first. So in the product rule, it will give you two terms, both of which will have e to the negative t in it. And then when you take a derivative of that, since both of them have e to the negative t, by the same argument, you'll have four terms, all of which have e to the negative t in it. Basically because an exponential's derivative is itself, which means that every term on the right-hand side, on the left-hand side, when you plug this in, will have e to the negative t in it, which is good because we have a term that's e to the negative t on the right-hand side. And so we have a way to control the fact that we have a bunch of e to the negative t terms. Some of the e to the negative t terms, the other part is subtle. So like when you take the derivative, when you do the product rule and you take the derivative of the e to the negative t, it's just going to pop out negative, and then it's going to e to the negative t. But when you take the derivative of this first polynomial right here, it will reduce it by 1 degree. So right now it's a linear, so it's like a naught a1t, but when you take a derivative, it would just be a1. And then that's going to be something that happens with x prime. X double prime, eventually you would have to probably take another derivative, and then there's going to be terms where this completely equals 0. So essentially on the left-hand side, you'll have all the terms have e to the negative t in it, some of which will be multiplied with 0, which will go away. Some of them which will be multiplied by a1, because when you took the derivative of the first polynomial once, it would have popped out an a1. Only the x term right here, actually, there will also be one of these because, the product rule says you do like derivative of the second times the first. So there will be terms that will keep the t term right here. So that means that all your terms on the left-hand side will be either e to the negative t multiplied by a constant or e to the negative t multiplied by t. Now we just need to make sure that when we plug this in, we find capital A naught and capital A1 such that all the terms that are just constant times e to the negative t vanish, and we're only left with t e to the negative t equal to 1 on the left-hand side, and you can do this. Now, we do need a general first-degree polynomial right here, because this, for instance, let's say the particular solution is not a degree 1, but let's just say it's just a constant. It's a constant, e to the negative t. This will not work because if you plug this into the left-hand side, you will never have a t times e to the negative t show up, right? If you imagine, this already has just a times e to the negative t. So we're not doing that. We're basically deleting the a1t term and just have a constant. So thinking, okay, this is a degree 1 polynomial, but what if we went 1 degree lower in our solution form for the polynomial in the particular solution? This will have no hope of resembling the right-hand side because there are going to be no terms on the left-hand side that has t e to the negative t. They'll have e to the negative t, but they won't have a t to the negative t. So you cannot go lower, although you could go higher. So you could say hypothetically you want to do this and say a naught plus a1t plus a2t squared times e to the negative t. This is okay technically, but there's going to be a bunch of terms on the left-hand side. If you plug this in, first of all, it'll be more work. But if you plug it into the left-hand side, there's going to be terms that are a2t squared e to the negative t. And there are no t squared e to the negative t on the right-hand side. So you will end up getting these are 0 anyways to force this to satisfy this differential equation. So if it's going to be 0 anyways, might as well not even include that term in your particular solution. So although this is okay, because it's more general, generally it's better to be more general. So it's okay, but it's unnecessary and it's kind of more work. So we're going to stick with just, the least amount of work possible, yet sufficient generality. So this means that I'm going to plug in a general first degree polynomial here. So this is I'll just say general first degree 1 polynomial. So if you do that, again, the hardest, well, let's do the homogeneous solution first. So we'll just say, we'll just define x of h. The characteristic equation was r squared plus r minus 2 is equal to 0. And then this factors to r minus 1 times r plus 2 is equal to 0. And therefore, your r is equal to 1 and negative 2. So your two distinct roots means that you have your homogeneous solution is just C1 e to the 1 times t plus C2 e to the negative 2 times t. That's your homogeneous solution. And the only reason I did this was because if you look at the particular solution, right? So if you look at the particular solution, you multiply this out, let's say, so you get a naught e to the negative t and then a1 t e to the negative t. There are going to be no terms that conflict with the homogeneous because this is a e to the negative t, this is e to a positive t, and this is a e to the negative 2t. So your particular solution form can just stay. And so basically, we're saying that it's a general first degree polynomial, a0 plus a1t times e to the negative t. And we're going to try to find a1 and a0. And this is going to be a pain because you'll have to do the product rule on this. So that's why I have space down here. So maybe I'll just grab this. This is what we have. This is the same equation. We're not going to get to plug it in yet because before you even plug it in, you need to compute the derivative. So I'll just say xp prime. This is even worse maybe than the other one that we had done. So again, you're going to be bored if I actually do the derivative of this using the product rule. So this ends up becoming, no, it's a negative t. So let's do this. I'm going to just screenshot this. Just do this. I can actually copy somewhere else that I've written. Okay, so then we have this, and then it's going to be minus t e to the negative t, which is, if you actually wrote it out, would be the first term is just a naught e to the negative t plus a1, 1 minus, because I'm just factoring out the e to the negative t. So this will be xp prime. Xp double prime is taking the derivative of this, which is going to be even more work. But this one is just going to pull out a negative. So it's going to be a naught e to the negative t. And then right here, you have to do the product rule. So you can take the a1 out. And then it'll be e to the negative e to the negative t minus 1 minus t e to the negative t, which if you factored out the e to the negative t on the second term, will end up being e to the negative t plus a1 t minus 2 e to the negative t. So, this you can definitely, I have full confidence that you can check on your own. It's just doing the product rule on this, and it's just going to be a little hard to probably follow immediately because I'm combining some terms and simplifying. But you can check, and if you find any mistakes, let me know. So that's the xp, then your xp prime and xp double prime, right? And so now what I'm going to do is just plug those in. So basically this right here is going to be your x double prime. So let's just plug in. That's x double prime. Plus this right here. So I'll just do this and then just say, because there's a minus sign already there, it's going to be that. Minus 2 times the xp by itself has to equal t e to the negative t. Okay, so first off, you could just divide everything by e to the negative t. Like every single term, there's 1, 2, 3, 4, 5 terms on the left-hand side, which are products that contain e to the negative t. So you can just divide everything by e to the negative t. Right? And then I'll just multiply things out. So the first term is just a naught. This one is going to be a1t minus 2a1. That's just distributing. This is just a naught plus this is a1 minus a1t minus 2a naught plus, oh no, actually minus 2a1t is equal to t. Okay, so there are these that cancel. So this a1t cancels with this one. This a naught cancels with this a naught. Okay, that's all we can do, I think. So we're left with, I'll just say that we have, so there's a minus 2a1, there's a plus a1, that becomes a minus a1, there's a minus 2a naught, and then there's a minus 2a1t is equal to t. All right, so that's all we have. Then we want to match, so we're going to say this has to match with that, and then this has to vanish. So from the orange one, we get negative 2a1 has to equal 1. Therefore, your a1 has to equal negative half. And your okay, so then your red one has to go to 0. So you're just going to have negative a1 minus 2a naught has to equal 0. But we know a1 is negative half. So it's going to become positive half here when you plug in negative half minus 2a naught is equal to 0. Then you're going to get negative 2a naught. Well, I'll just move it to the other side. So you get half is equal to 2a naught. So you divide both sides and you get a naught is equal to 1 over 4. And so we have our, what is it? So I'll just say our particular general solution is going to be this right here. So this is our particular solution that we had. But our a naught and a1, so that just means that we can just plug those in. So we get a naught was 1 over 4, it's the red one. And then we got a1 is equal to minus half. So this is our particular solution. Plus, our homogeneous was way up here that we had done. And that's our general solution. This is a painful problem if you actually were to, sit down and, I mean, obviously this looked like a pain because it blew up and had a lot of terms here. But also, there was a lot of work in computing XP prime and XP double prime behind the scenes, and I don't want to bore you guys. Otherwise, this problem will be just like the entire class period. But you get the process, right? It's a systematic process. It's sort of tedious. And so I feel like this whole section is not that hard. It's just tedious. You just, you have a solution form. You take the p prime, p double prime, xp double prime. You may do the product, need to do the product rule, and then you plug it in, and then you have all these terms that need to match on the left and the right hand turn. So it's like an algebra problem. But it's like, it's like a very systematic process. So, and what's neat about this is, like we said at the very beginning of the class, is like, what does it mean to be a solution to a differential equation? If you plug this green underlined thing into this differential equation, you should see that it satisfies it. Now, that's a lot of work if you want to check, and plug this into x double prime, which means you got to take the second derivatives and x prime and so forth. But you should get that this plugged into the left-hand side will give you t e to the negative t. And it's a general solution because it's not like you just found any one particular solution. You've now characterized the infinite family of solutions, because C1 and C2 can be arbitrary. So the goal of this class is to be able to get your hands on the general solution that satisfies this differential equation. And it turns out for second order equations, you have up to 2 degrees of sort of freedom where you can, set C1 and C2 to be any arbitrary thing. That's fine. So let's look at another case. So what did I do? I always like to just point out, like, all these problems I'm making up on my own, and I like to do a slight change to it. So here, what did we have? Before, it was x double prime x prime minus 2x is equal to t e to the negative t. There's a slight change. The left-hand side stays the same. This is equal to t e to the not negative t, but e to the positive t. See how that changes the problem. So the homogeneous solution will still stay the same. You're just going to have this stuff again. Because the left-hand side didn't change. I only changed the right-hand side. So your homogeneous solution is still going to have r squared plus r minus 2, all that business. So this homogeneous solution will stay the same. Now, your particular solution is going to be, this is what you would expect, right? Because now you have a t e to the negative t, e to the positive t here. So your particular solution, what did it used to be? I'll just copy what it used to be. This is what it used to be, right? This is what it used to be. But what do you think it's going to be now? Because you have t e to the t. This is still going to be a first-degree polynomial, a general first-degree polynomial. So your t is the first-degree polynomial. So you know it's going to be a naught a1 t. But this is e to the t. So you don't, instead of e to the negative t, like what we had before, it will just be e to the t instead. So that's what you'd expect to see. Now, if you say you multiply this out, you'll get a naught e to the t plus a1 t e to the t. Are there going to be issues do you predict there'll be issues with this particular solution? And why? So there's a term in here. So if you look at this term and this term, these match. And so this is going to cause an issue when we try to plug it in to this differential equation, because there is a term in the particular solution that matches with the term in the homogeneous solution. So the solution, the fix to this is to multiply by t. So I'll just say multiply by t. And that'll give you so xp that's going to be equal to, so if each term gets, the whole thing gets multiplied by t, you're going to get a naught t e to the t plus a1 t e to the t. And so this is going to be the correct solution form. Correct xp. Yes. Oh, yes. Sorry. T squared, because you're going to multiply this whole thing by t. So it's going to be the first one gets t, this one's going to t squared. So that's the correct solution form. Now, again, it's going to be a lot of work, and this is the last one that I'll probably do this level of work on. But if you were to compute the derivative and the first derivative and second derivative, which I'll write here, you'll get xp prime is equal to a naught plus 2a1 plus a naught t plus a1 t squared times e to the t. And then your xp double prime will end up being 2a1 plus 2a naught plus 4a1 plus, this is like after simplifying and combining some terms and stuff, so it's going to look really difficult for you to be able to see this just in this final form. But if you were to sit down and actually go through the trouble of doing the derivative of this, which unfortunately requires the product rule twice, because the first term requires a product rule, and the second term also requires a product rule. And so you'll have this thing blowing up. But then when you take the second derivative, there's like probably additional product rules, because you've got like, it just spawns more terms, because each time you do a product rule, one turns to two terms. And then it's just like, you're just getting all these terms. And so, and if you just combine things and stuff in the end, you can check that this will be something that you'll get for both the xp prime and xp double prime, right? That's just a Calc 1 exercise. So what do you do with that? I have another page here because I knew this is going to be so long. You're going to plug it in. So when you plug it in, you're going to have your xp double prime term is going to be 2a1 plus 2, I'll just copy and paste it, but I'll have to probably shrink it because it's too big probably to fit in one line. So I'll just take this, paste it, and well, maybe I can fit it, and then it'd be plus your xp prime is going to be this one minus 2 times this thing, because this is your xp. I'll just subtract this. All right, this is too big for me to write the right-hand side, so what I'll do is just take this and shrink it. Is equal to t e to the t. See, so all I did was just took this, that's x double prime, plus this, which is x prime, minus 2 times x, which is your corrected xp, which is the one that got multiplied by t. And now, okay, so you can just divide everything by e to the t again, because they're all these, there's three terms on the left-hand side. They all have e to the t, so you just divide. Of course, this right here, I didn't go through the trouble of factoring out the e to the t, but you can imagine that if you multiply these out, they would be two terms that have e to the positive t, and those get canceled. So you get this. And then I'm just going to write all the terms in the correct order here. And what I mean by correct order is I'll just write, well, I'll just write it just straight. So I'll just say this is going to equal 2a1 plus 2a naught. That's these two. And then you're going to have this, which is 4a1 plus a naught t plus a1 t squared. That's just writing all this. That's fine. And then you're going to get, I'll just copy and paste because it's just literally all this. You're going to add this. And then you're going to have minus 2a naught t, because this 2 multiplies, and then minus 2a1 t squared. This has to equal t e to the t. Okay. Now I'm going to, okay. So we should just be able to go ahead and do the algebra. So we have this, right? This t e to the t. Where are all my t terms? There's one here. There's this one right here. And there's this one right here. So all these oranges have to equal this. And then you need to, let's look at all the constant terms. So you have, these are constants, This is a constant. And so there's only two of those. Those have to go away. And then there are only a couple or few t squared terms. So this one's t squared, this one's t squared, and those have to go to 0. Is it good? Yes. Oh, sorry. Yeah, go away. So this is just t. Yeah, good. So this is gotta match with that. All right, so let's write the purple stuff. So let's do the t squared. This should all go away. So basically the a1 plus a1, just this one, plus this one, which I could have combined, minus 2a1 should equal 0, which I could already tell is just going to give you that it's just going to be 0 equals 0, which doesn't help us at all, but it is at least a true statement. Because if you have two a1s, but then minus a1, so this gives you a true statement, but doesn't help you in finding a1 and a0. Thankfully, there's only two coefficients. There's a0 and a1. So you don't need 3 equations, although it looks like you'll have 3 equations from this, because you'll have a purple equation, a red equation, and an orange equation. So you have more equations than unknowns. And so there might be one equation that's not helpful. It's just going to be like a true statement or a repeat of the others. And so you'll do the purple one. And then the orange one is the t. So these are the t squared. So let's do the t's. The t's are going to be 4a1 plus a0, just this one up here, plus this one right here is 2a1 plus a0. And then there's a minus a0. That all has to add up to t. This right here will give you a0. This is a plus a0, but a minus 2a0, so those go away. And you'll end up getting, or actually, I mean to be 1 here, right? And so this will end up giving you 4a1, 2a1, which is 6a1 is equal to 1. Therefore, your a1 is equal to 1 over 6. That gave us one of them. The red ones have to all disappear. So you have 2a1 plus 2a0 plus a0. That's it. Has to equal 0, which means that we have, okay, so the 1 over 6, okay, I'll just say that we know already. So this is like 1 over 6 here. So we're left with well, I'll just combine. So it'll just be 2. I'll just do it this way. So I'll just say, why is this computer? So I'll just do this later and then just say that we're just going to have 3. There's 2 plus 1. So this is 3a0 is equal to, and then I'll shove this to the other side. So it'll be negative 2a1. And then I'll just say that a0 has to equal, you're dividing by 3. So it'd be negative 2 over 3a1. Okay. And then I'll just say that your a1 is equal to 1/6. So I'll just do a little arrow and say this 1/6 goes in here. So it's going to be a0 is equal to 6 times 3 is 18, but then there's a negative 2 on the top and 18, and that's divisible to, so a0 is equal to 1 over 9. Okay, so we got our two coefficients for a1 and a0 that were in our corrected xp. So our original xp had to be multiplied by t, which made the derivatives painful. But if you plug those in and you try to solve for a1 and a0, we get a1 is this and a0 is this. And we're going to just use that to write our particular solution. So our particular solution is going to be this right here, but with our a1 and a0 equal to these things. So I'll just make an equal sign and say this a0 ends up becoming negative 1, 9. And then this a1 ends up becoming 1 over 6. And so with that being your particular solution, your general solution will end up being equal to like this negative 1/9 t e to the t plus the 1/6 t squared e to the t. That's your particular solution plus your homogeneous solution. We must have done that earlier. Here it is. That's your homogeneous solution. So what did we do? We ended up taking our equation, finding the homogeneous solution by just doing the characteristic on the left-hand side. Notice, and then we say our particular solution, because it's a polynomial times an exponential, will also be a general polynomial, degree 1 polynomial times the same exponential e to the t. However, one of those terms matches with the homogeneous, so if you plug this in, you'd have some kind of false statement or contradiction. The solution has always been multiplied the entire particular solution by t. This is your corrected xp. You take the derivative, the second derivative, plug those in, and then you match terms, and you end up getting your two coefficients. So that's like a really long example, but yeah, it's good to illustrate that, these are sort of a long process, could be a long process. You'd probably not have ones that are going to be like this on a test, but at least you know how it looks if you were to have one. Yeah.
So you might get an extension on the whole. I just can't look at a screen for very long without it hurting.
Yeah.
I didn't get it done by
Um,
Wednesday
so
or Tuesday.